Hey everybody, thanks for watching the video for chapter 3, compounds, how elements combine. All right, that's what we're going to be talking about now. So we're going to be talking about electrons. We talked a lot about neutrons, and now we're going to be talking a lot about electrons. So first, in this video, I want to try to cover sections 3.1 and 3.2, electron arrangements, and also ion formation. All right. And if some of those words like ion sound unfamiliar to you now, you're going to be familiar with that by the end of the video. Okay, so basically, why is water H2O? Why not H3O, H4O? Why do elements combine in the way that they combine? And the answer to that question is for stability. All right, there's an advantage to those electron rearrangements, and that advantage is stability. It's all about stability, okay? And so whenever we're thinking about stability in electron arrangements, we need to think about, well, where are those electrons in that atom that we talked about? So we have the nucleus here, the nucleus of an atom, and where are those electrons? Right there in the electron cloud. So here in the electron cloud, we're going to have a rearrangement of all these electrons, and they're moving around really fast. So there's all these electrons in here, just moving around. Okay, so fast. We can't tell exactly where in the electron cloud the electrons are. They're just moving around. They don't fill up the electron cloud. They're just moving so quickly. Okay, so you know that. And think about these electrons in terms of energy. They're constantly moving around, all right? That's a lot of heat. That's a lot of energy happening, all right? So you have this kinetic activity going on, all right? You have this constant motion. So understand this in these terms, because this is going to be relevant with the arrangement of these electrons and the stability that they have in an atom. And one way that you can think of all of this is sort of like a staircase. Okay, so let's think of it this way. Consider the nucleus of an atom to be the base of this staircase. So this is the staircase base, and this is the nucleus of an atom. And maybe you want to think of these stairs as more circular. Okay, so these are energy levels. These are principal energy levels. Right, and these are where the electrons are going to sit at. So the electrons that are going to be farther away from the nucleus, the electrons that are farther away from the nucleus have more energy. All right, and the closer you are to the nucleus, the less energy those electrons have. So as you can see right here, like on this first step, that would be the lower energy. Okay, so that's one way to think about it. Okay, and so on each one of these steps, all right, on each one of these steps, these energy levels in the atom, only a certain number of electrons have room to sit. So on this first level, you're only going to have 2 electrons, right? And then you have another level, and only a certain number of electrons are going to sit there, and so on the 3rd, 4th, 5th levels. All right. So more electrons are going to want to be as close to the nucleus as they can. So if you have 3 electrons, 2 are going to be able to sit on this stair, and then the next electron that needs to sit is going to want to be as close as it can be to the nucleus. And so it'll sit right here on this next step in the next principal energy level. Okay. right? So you can think of it this way, all right? And in terms of energy, notice it's not the same if you understand it in terms of the lengths of these stairs, all right? So that principal energy level is, it changes a little bit the farther you get away from the nucleus, okay? And so basically, here's just the text on this slide that sort of goes over what I was talking about. The electrons are only going to occupy certain energy levels or steps on that staircase, okay? They cannot be in between the steps, okay? They cannot be in between those energy levels. They have to be there on one of those steps, okay? So those electrons are going to occupy the lowest energy level first. It's closest to the nucleus. Think of that staircase, all right? The base of the staircase is the nucleus. So they want to get as close as they can to the base first, right? So, and once again, to reiterate that unlike a real staircase, that staircase you notice had differences in the height of each step as you go. So the energy levels closer, as the energy levels get closer together, the farther away you get from the nucleus, all right? You noticed that. So that has to do with how much energy is going to be at that energy level, okay? And so once again, you can see what I mean. And one thing that we have to think about is what I said before. What do all of these electrons want to do? What do all of these atoms with their electrons, what do they want? They want stability, okay? So if you think about the periodic table, let me pull up a table. All right, here we have a periodic table. You see there's a lot more to the arrangement of these elements that we're learning as we go. There's a lot of information packed into this table. And so you see that over here, we have helium, all right? And over here we have hydrogen, all right? And so the placement of these elements on the table tells us a lot about the electrons that they have and how they behave and what energy levels they're on just by their placement on the table. So if we take hydrogen, all right, and helium, we know that hydrogen has one proton, but it also has one electron, right? And helium has two electrons. Okay, we can see that, right? Because we know that this is both the number of protons, and in a neutral atom, that's also the number of electrons, right? Okay, so if we think about that this way, we know that elements that are going to appear in this first group have one electron, all right? And if you have atoms that appear in this first period, this is going to tell you information about where, what are the number of electrons in the highest energy level for that particular element. But that may sound a little confusing at first. So what do I mean by the max number of electrons in an energy level for an atom of an element? So let's go back to our PowerPoint. Let's see. So when we're trying to figure out the maximum number of electrons that can be found in a given energy level for an atom of an element, you can use a formula for that. All right, and so the formula is going to be 2n squared. All right, so n N is the number of the energy level, okay? So let's see if this works out. All right, let's see if this checks out. So let's say if we have, so let's say if we're talking about our first energy level, all right, and we can think of this as that first period. That's kind of why I wanted to show y'all a little bit. So if you think of your first energy level, all right, so you're going to have 2 multiplied by 1 squared, or squared means 2 multiplied by 1 multiplied by 1. Okay, so your answer is 2. So that means that is the maximum number of electrons that can be found in that energy level. All right, so in the first energy level, all right, 1, for the first energy level, the maximum number of electrons that can be present is 2. Okay, so if you have 2 electrons that are filling up that energy level, you're going to have some stability going on. And if that atom is more stable, it's less reactive, it's complete, it's comfortable. All right. So we're going to look more again at the periodic table so that you can be kind of familiar with this and what this all means. But let's just see if this all checks out with the formula. All right, so second energy level, all right, N of 2. So our second energy level, and you're going to see this is really going to be, we're going to have our second period. So in our second energy level, all right, we're going to see 2 times 2 squared. So that's 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So here you can have 8 electrons in the highest energy level. And so you'll have atoms that have a total of 8 electrons in that highest energy level. And once again, those are going to be stable atoms of that element. Okay, those elements are going to have very stable atoms. They're not going to be very reactive. And in the third energy level, let's see, 2 times 3 squared. So you have 2 times 3 equals, what's that? That's going to be 18 electrons in the highest energy level, in the highest level. All right. So, or for that energy level, rather. Okay, so it does check out. So in the third energy level, the maximum number of electrons is 18, and so on and so forth for the energy levels for 4 and 5. Do the same thing. And as I told you, there's a lot packed into the arrangement of the periodic table. It tells you a lot about the electron arrangement. All right. So one thing that I was talking about would be the octet rule, but I'm going to give you a clear definition of that. So basically, when I was saying if you're going to fill that energy level, like we were just talking about with 8 electrons, or so on and so forth, if you fill that highest energy level with 8 electrons, that's going to be a very stable atom. And that is what these atoms of these elements are trying to achieve, stability. All right. And so here is a table of the periodic table. So you have hydrogen and helium, lithium, beryllium, and you have all of these group numbers, and you have the total number of electrons, which are going to be equal to the total number of protons. So it's the atomic number that you're going to see on the periodic table, right? And so based on their placement, their group number and their period number, it's going to tell you a lot. All right. So the number of electrons that are going to be in energy level 1 for hydrogen is going to be 1. For helium, lithium, and beryllium, it's 2. All right, so that is the number of electrons in the energy level for 1. All right. And then lithium is going to have electrons in 2, and beryllium is going to have 2 electrons in the second energy level. All right. So let's look at the periodic table that we just had pulled up here. So, all right, so we see hydrogen here is going to have 1 electron, and helium has 2 electrons. And so they have these electrons in the first energy level. All right, so lithium, I'm going to erase so that you can see a little better. So lithium also has filled that highest energy level with 2 electrons, but it has a 3rd electron, so it sits on the next step. And the next step is going to be that next period. Okay, so that's what I was trying to explain to you guys. And then beryllium has 2 electrons that sit on that first step already, and they move to the next energy level. Think that's the second step, a little farther away from the nucleus and from the base of the staircase. So that's 4 electrons here. So 2 electrons have already filled up the first staircase, and 2 electrons are sitting on that second step. All right, so you can see by the arrangement of the atomic number, it tells you where those electrons are. All right, so there really is a lot of meaning there, and that's basically what this table is telling you, and so on and so forth. All right, and it tells you that for the main elements, you can figure out a lot in general for the main elements. For the transition elements end up being a little bit different with the way they're going to share these electrons. All right, so you have your table continued for those elements. And so this is a good table to always refer back to make sure you understand. All right, so something that is interesting that the group number tells you, it tells you the number of electrons. It tells you the number of electrons that you're going to have in each energy level. But the group number itself is going to tell you exactly the number of electrons in that highest energy level on the staircase, right? Farthest away from the nucleus. All right, so your group number is going to tell you the number of electrons that are in that higher energy level. Okay, so you have magnesium here. All right, that's in group 2A. And that's going to tell you that they have 2 electrons in the 3rd energy level. All right, so every time we are filling up one of those energy levels, we are going to another period. Okay, so let's see where magnesium is on the periodic table. All right, so magnesium is right here. Magnesium has the atomic number 12, so it has 12 protons and 12 electrons, all right, if it has a neutral charge. And so you know that magnesium has filled these levels on the staircase, has filled these levels of away from the nucleus of the atom with electrons, and has made it to the next energy level, the 3rd energy level. And that's the highest energy level in the group number. So this is the highest energy level it's at the 3rd energy level. The period number is going to tell you that. And the group number is telling you that there are 2 electrons in that level. All right, so because of the period number 3, we know that in that 3rd energy level, we are going to have 2 electrons. All right, so we did our math. We know the maximum electrons that can go in each level. So magnesium has a total of 12 electrons. So 2 of them are going to sit in that first level close to the nucleus as they want to do. All right, so then you're going to have 10 left. All right, okay, so you're going to have 2 in that first level, then you're going to have 10 left, 8 of those are going to be able to sit in the next level, and then 2 are going to be left. They're going to sit in the third level. All right. So here you have an energy level that is not full, and it's not satiated. So you're going to have something that is reactive. All right. So basically, when you look at the periodic table, when you have a group whose highest energy level is filled, those are going to be stable. Those are going to be some really stable elements. All right. And so they're going to be less reactive and not reactive in most situations. But I'm getting ahead of myself on the PowerPoint. So you can learn a lot from this table. All right. The groups and the periods tell you quite a lot about the electron configuration. Okay. Just the arrangement of the electrons. So being able to understand the number of electrons present and where they're present in each energy level is going to tell you something about the characteristics of those elements and their relationship to nearby elements. Okay, so it's giving you some insight of how the elements relate to each other. Okay, so elements that are in the same group on the periodic table are going to have the same number of electrons in their highest energy level. All right, that's basically what I was just telling you. All right, so elements in the same group have the same number of electrons in their highest energy level. Okay, so you can really get a lot from the periodic table. So if we look at boron and aluminum as examples, they have 3 electrons in their highest energy level. They're in group 3A. All right, let's see, is that true? Aluminum and boron, all right, they're in group 3A. So both in their highest energy level, they both have 3 electrons, but their highest energy level that they have is different. One is going to go to energy level 2, boron, and aluminum goes to energy level 3. Okay. So boron, all right, boron and aluminum, they are both group 3A, and that means both of them have 3 in their maximal energy level. All right, they just have different levels for where those 3 electrons are going to sit. All right, and so you may notice that both boron and aluminum have those different atomic numbers, and so you know what they have in common, and you know what they have different about them. All right, these are going to be in different upper energy levels. Okay, but they're going to have the same number of electrons in that upper energy level. Okay, it's very interesting, but it could be a tad confusing, so be careful. Make sure you get this right. Okay, so the highest energy level that contains electrons, we're going to call that the valence shell. All right, so that's why I just wrote VE. So it's kind of the way I'm going to abbreviate the valence electrons. So the electrons in that valence shell are valence electron, right? The electrons in the highest energy level. Just repeat yourself so that you can remember these definitions, because they're going to probably be on your exam. All right. So valence electrons are the ones that are farthest away from the nucleus. All right. The electrons that are present for the atom of that element, but farthest away from the nucleus, farthest away from the base of that staircase. Those are going to be the valence ones. Those are going to be the electrons that are reacting, okay, that are reacting or participating whenever we're talking about building compounds and so on and so forth. So groups, once again, just to sort of clarify, those indicate the number of valence electrons. All right, so when I kept saying the number of electrons in that uppermost energy level, you can just say valence electrons, because now you know that definition, you know what valence electrons means. And periods indicate what is the outermost energy level. So if you look at the group number and the period number, you say, well, the outermost energy level is 3. And there are, if you look at the group, it's 2A, you know that there are 2 valence electrons in that third energy level, okay? And so this is a condensed table, all right? So let's just take an example here. Calcium right here. So it's a condensed table. So when we're thinking of these rules, we're not including the transition elements. So we're looking at these elements in this condensed table to where these rules apply. And let's see, we have calcium. So we have some metals here. We have some non-metals, showing you where they're pulling from in this particular illustration. But let's talk about calcium. All right. So if we've got calcium, we see that that is in group 2A, and that's in period 4. So we know that there are 2 valence electrons that are in the 4th energy level. All right. So you see that it's pretty powerful. You get all of that information there. All right. So you see that this element is going to be reactive because they haven't filled that 4th energy level. All right. And you know that they want to fill that energy level. They want to be stable. They want to be complete. All right. So this is going to be in contrast with the elements that are on this end of the periodic table. So the elements that are on this end of the periodic table, as I said, they're going to be very stable and non-reactive because they have filled their highest energy level. They have filled their highest energy level. They filled their highest stair that they have electrons to fill. Okay, so those are very stable. So that's why helium, even though is different from this rule, helium has 2 electrons, but it's very stable because it filled that first staircase that can fit only 2 electrons. Okay, so that's why helium is over here. Like someone asked that question on the first or second day of class, and it has to do with the electron configuration of helium. So even though they have 2 and it's only the first energy level, that is still full. So helium is happy over here. Okay. So once again, just get really familiar with what the periodic table means. All right. So basically, where you have neon and argon, they're going to have 8 valence electrons in their highest energy level. The period for neon is 2. So it's going to have 8 valence electrons in the energy level that is number 2. And argon is going to have 8 valence electrons in the 3rd energy level. Okay. So I think it all makes a whole lot of sense, actually. All right. And so all of the elements want to become complete. All right. So wanting to become complete has a lot to do with something called the octet rule. Okay. So octet, all right, that means 8. So the elements in group 8A, those are the ones with 8 valence electrons in their highest energy level. Those are the noble or the inert gases. All right, so they are mostly unreactive. All right, they're pretty satisfied. They are complete. All right, that energy level is complete for those elements. Okay, so oct, 8. 8 valence electrons, except for helium, which is happy with the 2 valence electrons because that's what's going to fit closest to the nucleus on that energy level. All right, so that is a very stable state for an atom. And the elements, the groups that are farther away from 8, those are going to be more reactive. Okay, reactive because they want to achieve 8 electrons in their valence shell. They want to be full, they want to be happy, they want to be complete. Wanting to be complete and to have 8 electrons in your outer valence shell, that is called the octet rule. Okay, so how are they going to do this? How are they going to become an octet as far as their electrons go? Some are going to give away electrons, some are going to take, some are going to share electrons. All right, so those are different ways of achieving valence and achieving the octet status that they're all going for. And whenever trying to reach this status, this advantage, we're going to form different kinds of compounds. Okay, and so we're going to solve some problems before we get into 3.2. Okay, so let's see. Here we go. So let's do 3.1, I believe. Okay. How many electrons are in each energy level of the following elements? So energy level. So that means the period. Each time we fill an energy level, we're creating a new period on the table. Okay. So helium, we know that one, right? Where's that one on the periodic table? All right. That is in the what? Let's see, maybe I could draw this out to make this easier. Let's make a little table. Let's say, so here we're going to have the total electrons. Here we're going to have the first energy level, second energy level, third energy level. All right. So let's say for helium. All right, the total, what is the total number of electrons for each element? For helium, we know that there are 2. All right, and how many electrons can the first energy level hold? Well, that was, we can use our formula, 2 times 1 to the 2. So you just go find the group number, the period number for helium, which is 1, and you multiply it out. And you have, that is the maximum number of electrons that are in that valence shell. All right, so in the first valence shell, you have 2. Okay, so that's why helium is happy. We are finished. There is nothing in the second and third energy levels for helium. So let's do carbon. Okay, carbon. So how many electrons are there? So we know the atomic number for carbon, right? That's the number of protons, which is 6. All right, so we can write that here. So the total number is 6. We know in that first energy level, as we just did the math over here, we can only fit 2 electrons. So 2 of them are definitely going to go there because that's where they want to be. And so 6 minus 2 gives you how many are left? 4. And 4 can fit here. Because if you're looking at the second energy level or the second period, you can do that math. And you see that you can fit 80 electrons. So you definitely can fit 4 in that second energy level. And you're done. So now we can do sodium. Sodium has 11 electrons. So that's the atomic number. Okay, you know how to find that. So you can fit 2 of those electrons where they want to be. And 11 minus 2 is 9. Well, you can only fit 8 on the second energy level. So you're going to write 8, right? And then you have 1 left, right? Because 8 plus 2 is 10. So you need to get to 11. So you have 1 electron on that third energy level. Okay, and then you have neon. All right, so neon has a total of 10 electrons. All right, so in the first energy level, you're gonna have how many? 2. In the second energy level, you're just gonna have 8. So there you go. And that's really all you need to know. How many electrons are in each energy level? There you go. So let's do 3.3. How many valence electrons are present in the following atoms? All right. How many valence electrons? Okay, so let's see. We're going to do nitrogen. So how many valence electrons are present in the following atoms? So let's see. Let's look at a periodic table. All right, so we're looking for nitrogen. Here's nitrogen. So how many valence electrons are we going to have? All right, so we know we have 2 energy levels because it's in period 2, and the number of valence electrons is in the group number. So that is 5A. So that is going to be 5, right? So it's in group 5A. The group tells you the maximum number of electrons in that highest energy level. So it's group 5A, you're going to have 5 electrons. There you go, nitrogen. Okay. So, or you can just write it this way so that you know exactly what you're talking about. Boron. What group is boron in? Boron, let's go take a look. Oh, wrong thing. Boron is in group 3A. All right, so boron is going to have how many? How many valence electrons? It's group 3A. That's going to be 3 valence electrons. Okay, silicon. That is going to be 4, group 4A. So that's going to be 4 valence electrons. Let's see. Silicon. Yep, silicon, group 4A. All right, let's go back to our problems. Potassium. All right, that's going to be 1A. So you have 1 valence electron, right? So if you don't have the octet, that gives you an indication of their behavior and how reactive they are. Okay, that's what I mean by it tells you about its behavior relative to other elements. All right, so let's do 3.5. Which of the following elements are stable as atoms? Okay, let's see. So we have hydrogen. All right, is hydrogen stable? You can think about what side of the periodic table hydrogen is on. What is that on, the left side or the right side? Is it on the right side where everything's stable? It's on the left side, so I don't think it's going to be stable. Okay, so what is the group number? That will tell you the number of electrons, the valence electrons, okay? That's the number of electrons that are in the highest energy level that electrons fill for atoms of that element. And for hydrogen, that's going to be group 1A. So you know that there's 1 valence electron there. So that is unstable. All right. It's unhappy. It wants to get happy and make compounds so that it can be more stable. It wants to form an octet. Okay. It wants to fill those energy levels. Okay. So B. All right. B, nitrogen. Let's see where we are. Nitrogen. That's 5A. We just did that one, right? So that's 5 valence electrons. So that's going to be not very stable, right? Once again, not stable, sad face, and wants to get happy. Neon, that's going to be what group? 8A. That's in our group of noble and inert gases, right? So that's unreactive. So that's 8 valence electrons filled that shell. So that is stable. It's happy. It's not reactive. It's fine the way it is. Sodium, Na. All right. So that is 1A. That's going to be very reactive, right? It's going to want to react with certain other elements, right? It's going to get it where it wants to be. Oop. Mistake. one valence electron, and that is unstable. So our only stable one was neon. All right, so, all right, our next section of problems is 3.2. So let's do a little introduction to 3.2. So we're talking about how are we going to form those octets, okay? So the way they're going to do that, an atom is either going to gain or lose electrons, okay? And the newly formed particle is going to have an unequal number of protons and electrons, all right? So before we talked about atoms that have an equal number, so when atoms have an equal number of protons and electrons, that is going to be a neutral charge. That's going to be neutral, all right? It's no charge. Neutral charge, no charge, okay? But whenever you have an unequal number of protons and electrons, you're going to have a charge. Those are going to be charged atoms, and they're going to be called ions. Ions are charged atoms, okay? So you're either going to have positively or negatively charged atoms whenever you have an ion, okay? So whenever you have a negatively charged atom, that's going to be called an anion. Anion. Get familiar with that. Anion is negative. And when you're going to have a positively charged atom, that's going to be a cation. So anion, negative. Cation, that's positive. Write it out for yourself. Okay. So if you have this chlorine atom, all right, so you have chlorine on the periodic table. Let's see. You're going to have your atomic number 17. So usually you have 17 protons and 17 electrons. Okay. So chlorine. So chlorine wants to become an octet. Okay, chlorine wants to become an octet. So how is it going to do that? You have to think about how many electrons or valence electrons chlorine has. How many electrons are in that highest energy level? Okay, so basically, when you look at the periodic table and you do the math, you can see that chlorine, let's look at the periodic table. Chlorine is right next to argon, all right? So what can it do? It can either lose several electrons or it can gain electrons. Can gain electrons. So either lose 7 electrons or can gain 1 electron and then have 18 electrons. Okay. The thing about losing 7 electrons is that this is a lot of energy, right? It's going to require a lot of energy. So instead, we're going to gain 1 electron. All right, so you have your 17 protons and your 17 electrons, and you're going to gain an electron. All right, so you're going to try to satiate those energy levels. So you gain an electron. So here you have an electron. All right, and you're going to have 17 protons and 18 electrons. So that's what these ions are. The proton number is not going to change. The electron number is going to change, right? They're going to be these atoms with these different numbers of electrons, all right? So here, this is what you're going to have whenever you're having this chlorine ion, okay? So the chlorine ion electron configuration is going to look like what? It's going to look like another atom of an element that has 18 electrons, all right? It's going to look like argon, its next door neighbor, okay? So it's right there next to that stable neighbor, and it wants to be like that. It's going to be like argon, and that means that they are isoelectric, okay? So basically, I'll tell you what isoelectric means. this chlorine is going to be denoted this way, right? So when we're talking about the chlorine ion, it's going to have this understood negative charge, okay? Because it has one more electron than it does protons. So now it has a negative charge. This is an anion, right? So you see that right here. 17 protons, 18 electrons. It's a negative charge. And so as I was just telling you, that whenever you have an atom of an element gain an electron, or what we're going to talk about next with cations, when an atom's going to lose electrons, when it becomes something more like the atoms of another element, then that atom is going to become isoelectric to another element. So that chlorine with the electrons was starting to have a configuration that appeared similar to argon. So you would say that chlorine, this chlorine ion is, or a chlorine is an anion, is isoelectric to argon. Okay, just regular argon. So iso means same, all right? Electric, it's like electron. So same electrons, they're isoelectric. All right, but when an ion has the same number of electrons as the nearest noble gas on the periodic table, it's said to be isoelectronic with that noble gas. So think that in particular. Isoelectronic with that noble gas. All right. So we're going to be talking about either something that is just one before or one after that noble gas on the periodic table. Okay. One before, one after. Basically, I'm talking about the atomic number, right? I'm talking about the number of electrons. So the ions are formed when the atoms lose electrons and become positively charged in the case of a cation. Okay, so this is a positively charged ion. So we take sodium, all right? Sodium on the periodic table. It's atomic number 11. When it's neutral, you have 11 protons and 11 electrons, all right? But sodium can do different things. Okay, it can either, so something that would be easy, it can just sodium can just lose one valence, here's sodium, and it can just lose one valence electron and be isoelectric with another element. Okay. So basically, you lose one of the valence electrons, and then you would become an atom that is more satiated for that highest energy level. Okay. So basically, you do this and you have, so if you lose one valence electron, you lose one, you get rid of one, then you have 10 valence electrons, or you have 10 electrons, not valence electrons. You have 10 electrons and you have 11 protons. Then you have a positive charge because you have one more proton than you do electrons. You have one more proton. So then you have a positive charge. You got rid of that valence electron, and you would write this as the chemical symbol plus, right? It's got a positive charge, one more proton than electron. It's not neutral anymore, right? And so these are things that you'll notice about the periodic table, all right? What the groups are going to tell you, whether it's 1A, 2A, or 3A. So groups that are in those main element groups on the table are going to form cations, right? With a charge equal to the group number. Okay, so what do I mean? What do I mean by that? Basically, if you have group 1A, you're going to end up with something with a positive 1 charge. Group 2A, you're going to end up with something with a positive 2 charge. Group 3A, you're going to end up with something with a positive 3 charge. All right. Okay, so what do I mean by that? So let's say lithium, all right? It would be easier to lose one of those electrons. So then lithium, if it loses an electron so that it can fill that highest energy level, it's going to end up with a positive 1 charge, and it's in group A. Beryllium, it's going to lose 2 of those electrons, those valence electrons, to be able to go to that previous energy level and have a filled valence electron shell. So basically you're going to lose 2 electrons. So for beryllium, you're going to end up with a positive 2 charge because you're going to lose 2 electrons. You're going to go to that previous period. Okay. So for aluminum, all right, let's find aluminum. Okay. So it can either gain several electrons or it can lose 3 electrons, which is easier, less energy, and then you're going to have a positive 3 charge for aluminum. Okay. All right, I hope you're following. If you don't, you can pause and rewind the video. Remember that. So this is going to be different for groups 5A, 6A, and 7A. All right, they're going to form anions. Okay. So that's the negative ion with a charge equal to 8 minus the group number. Okay. 8 minus the group number. 8 subtracted from the group number. So if it's 5A minus 8, so we're gonna look at a minus 3 charge. All right. And if we have 6 minus 8, we're gonna have a minus 2 charge. All right. And if we're gonna have 7 minus 8, we're gonna have a minus 1 charge for that anion. Okay. So here we're talking cations in groups 1 through 3. And here we're talking anions, all right? It has to do with the energy it's going to take to lose or gain those electrons, okay? So 4A, that's going to be a little bit different. But for 5, 6, and 7A, you can use this general rule, right? So basically, the transition elements are going to be the transition metals, more specifically, can form more than 1 ion. So you can't just determine that with this simple formula. But whenever you need to determine this, I'm going to help you out with that. All right. So polyatomic ions, what does that? Poly means many. All right. Many atoms. All right. Polyatomic ions, right? So basically, this is for the group of nonmetals. This is what happens whenever they form an ion where they can have several atoms put together. All right. So whenever this is happening, the charge for the entire group of atoms is going to be the same. So an example of that would be like if you have HCO3. So this negative charge, that's going to apply for that entire group. All right. So for that compound, so it's a polyatomic ion. Okay. So there you have an example of that. So when you start to think of the table in these relative ways, metals, nonmetals, polyatomic ions, it's going to help you whenever you're trying to name these ions, when you're trying to write down what that actual name for that element or compound is. Okay. All right. So whenever we're talking about atoms of an element in ion terms, we need to be specific. You don't then just say rubidium, you're going to say rubidium ion or cesium ion, sodium ion, lithium ion. All right, so you're going to make sure that you're specific to what you're talking about if you're not just talking about that element. If you're talking about an ion, you need to say so. So I mentioned earlier that the transition elements were different, like we have iron here. Okay, so what's going to happen is you're going to have to specify the electron rearrangement. So with iron, if you're going to lose the 2 electrons, you're going to have a positive 2 charge. You're going to write that as iron. You have transition metal, so that's going to be iron 2. You have to know your Roman numerals. Ion. And there you go. And so you know you have this cation. Okay, so you're going to be able to say it like that. All right. So here's just a table that's going to sort of help you out with naming some of these different elements in the form of the ion that they exist in. And so you don't have to memorize this table. Okay, this is just something for you to refer to. But as I was starting to mention before on that other table, on that table before the actual periodic table, these are ways of naming ions. So for the metal ions, so that's whatever is in blue. Okay, so that's a lot of the things on the left side of the periodic table, right? So for the metals, we're going to add the word ion. Okay, so sodium, that's in group 1A. That's definitely a metal. That's definitely on the left side. And you can look at the periodic table. That's an ion. So that's a sodium ion. And it's going to more likely lose an electron right there. Right? So sodium ion. Right? The transition metals, they're going to form more than one ion. They're going to rearrange in different ways. And so you're going to have to be specific about that. So you have to use a Roman numeral in the parentheses, and that's going to indicate how many of whatever electron was gained or lost. So let's say indicate the charge on the ion, just a note. So if we have iron 3, we're going to write that. We're going to write that as, we're going to just write the name of the element, iron. We're going to write parentheses 3, and that's an ion because it's a metal, right? So the rule for metal ions applies. Okay. So that gives you some repetition. Now we did iron 2 and iron 3. And for the nonmetals, the suffix "ide," all right, IDE is going to replace the last few letters in the name of the element, like fluoride. So we usually keep that first syllable, and then you add "ide" at the end. Chloride, fluoride, all right? So most polyatomic ions end in ATE, okay? So you're going to see some examples of that, and some are going to end in ITE, ite, and that means that they have fewer oxygen, one fewer oxygen in the atom, right? So that's how those ions are related. So basically, if you have sulfate, you have SO oxygen, you have 4 of them, okay? But if you're going to have sulfite, right? All right. But no, remember that here you'll just have sulfur. All right. And that if you have this negative charge on sulfur, you have sulfide. All right. Because of where it is on the periodic table and because of what it is, non-metal. Okay. And so you have some examples of these polyatomic ions. Of course, cyanide is an exception to hydroxide, hydronium. You just have to keep track of that. You just have to make it only slightly tricky. Okay. And so here you have some examples of some of the functions of ions, cations and anions. You have to use this to regulate fluids outside of your cells, to maintain ion concentration inside of your cells, all right, to have a heartbeat, right? So if you have any dysregulation with these ions in your body, you're going to interfere with your heartbeat and quite easily. So this has to be very tightly regulated, right? So they're not just these abstract things. Cations and anions are real, and you have to consider those. Okay, so we're not going to do 3.3 in the video. We are going to, and feel free to pause between 3.1 and 3.2 if you want. So we're going to do some more problems. All right, 3.2, 3.7. What is the difference between a metal atom and its cation? All right, so let's see the difference between a metal atom and its cation. All right, well, so for metal atoms, we have the number of protons is going to equal the number of electrons, all right? But we're going to lose an electron to get to that almighty octet, that stability that we want, the advantage of that arrangement and the stability and the decrease in reactivity that you would have to get there, you'd have once you get there. Okay, so then you would have a more positive, net positive charge. All right, and so when you make that ion, it's a positive ion, that's a cation. All right, cation, cats are positive. That's really silly, but whatever it takes for you to remember. Okay, 3.9. How are the names of names of a non-metal atom and its anion different? Okay, so nonmetals, that's yellow on the periodic table. All right, so you're going to have your atom, right? So that's you're going to have your element name. All right, so you have your non-metal atom. And for the anion, you're going to add "-ide" to the end. All right, we just went over that. Okay. So 3.11, calcium. All right. Provide the charge when an ion is formed from each of the following. So first is calcium. What's going to be the charge when an ion is formed? All right. So calcium is in group 2, 2A. So we know that that's just going to be +2, right? We went over that. So that's going to lose 2 electrons, and it's going to be right there as far as the electrons go in the previous upper energy level, all right, so that it can have its valence electrons filled up, okay? So it's going to lose those 2 electrons that has it on that other energy level, okay? So it's going to gain 2. So if it's group 2A, remember 1A, it's going to be +1, 2A, +2, 3A, +3. All right, so let's look at oxygen. Let's see what oxygen is on the periodic table. Okay, oxygen is group 6A. Okay, so it can either lose several or it can gain a few. So 6A is different. So what you're going to do is you can do 6 minus 8. All right, and then you would get a -2. So 6 minus 8, -2. All right, they're just trying to get to an electron configuration where they have that outermost energy level filled. Okay, so it's easy to just gain a few electrons for oxygen. It's really close to that end of the periodic table that's stable. Okay, so nitrogen. What's nitrogen going to do? Well, where is nitrogen? All right, here it is. It's 5A. So you can just gain 3 more electrons, right? That looks easy right there. So you're just going to gain 3 electrons. So you're just going to have a -3 charge. So for potassium, all right, that's in group 1A. So what is that going to be? That's going to be a +1 charge. All it has to do is lose 1 electron. So then it's a little more positive, right? It lost the negative. So it's a little more positive. Exactly 1 positive. Positive 1. 3.13. How many protons and electrons are present in the following ions? Okay, these are pretty easy, right? Okay, so let's say down here, we'll start with what they ordinarily have, protons and electrons. So for magnesium, normally magnesium has how many protons and electrons? 12. All right, so we have 12 electrons, right? And let's make a little table up here of what the protons and electrons are going to be in this scenario. All right, so for magnesium, oxygen, chlorine, and copper. All right, so we're going to have 12 ordinarily in a neutral atom, but whenever we have this ion with the different number of electrons, because that's what an ion is, we are going to have, let's see, if we have magnesium +2, that means we lost a few electrons. Okay, so that's going to be -2. That's going to be this -2. So we have 10 electrons here, right? 10, and we're going to have the same number of protons because the number of protons doesn't change if it's that same element, right? So that's not going to change. So oxygen, all right, the number of protons and electrons in a neutral atom are going to be 8. So the number of protons in the ion doesn't change, but we have a -2 here, a -2. That means we what? We gained some electrons. So that's going to go up, right? So we're going to have 2 more electrons, all right? So it's opposite of this sign that you see here, right? You have to think you're looking at a negative charge. We're talking about electrons. So chlorine, all right? So you have how many protons and how many electrons? 17 and 17. Look at your periodic table, the atomic number. So the number of protons is not going to change. The number of electrons is going to change, all right? You have a negative charge. So you added an electron. So it's going to be 17 plus 1 negative charge, 18. 18 electrons. All right, you see how it goes? You see how it is? Copper, all right? You're going to have 29 and 29, but you have a positive charge, so you lost 2 electrons. You lost 2 of them, so you're going to subtract 2. All right, so that's going to give you 27 electrons, and you're going to have 29 protons. So you have more protons, so you're positive. Like with chlorine, you have more electrons, you're negative. With oxygen, you have more of a negative charge, so you have more electrons. With magnesium, you have more positive charge, so you have more protons. So it makes sense. All right. So let's move along. All right, 3.15. Name the ions in problem 3.13. Okay, they listed them again. All right, magnesium. Okay, so how are we going to write out this magnesium ion? So you have to pay attention to metals and nonmetals. So think of metals. What's nonmetal? All right. So if they're metal, you're going to say ion. If they're nonmetal, you're going to say ide. All right. So magnesium. All right. So we have a metal here. So we're just going to say magnesium ion. There you go. Magnesium ion. All right. So here we've got this oxygen ion with this -2 charge. So that's just we're going to keep the first syllable, ox, and that's a nonmetal. Ide, that's an oxide. All right, chlorine. we have this negative chlorine anion. So what are we going to do? Is it a metal or a non-metal? It's a non-metal. You're going to write chloride. Chloride. Terrible speller. Okay, so for copper, right, we have this cation. So what are we going to write? It's a metal. So we're going to write out the word copper, the element. All right. We know that we have different rearrangements of electrons here. We're going to have a positive 2 charge. So we're going to put 2. And we're going to write ion. Right? That's it. Those are kind of fun, right? Okay. So 3.19. I think we're almost done. We just have 1 or 2 more. Or I guess we could do 3.18 also, but we'll do that even one in class. All right, name the following ions. All right, so these, you're going to use that table for these. Okay, so just look at the table. All right, so for A, look at your table. This is ammonium. All right, for B, this is acetate. And here we have cyanide. All right, so you have your polyatomic ions. So remember, you're going to have a table for these. All right, I'm going to help you with those. All right, so only polyatomic ions. This is the only, whoops. Trying to tell you that this is the only polyatomic ion, excuse me, I'm tired today, that is going to end in "ide." All right, because that's confusing. Why "ide"? We have other rules for "ide." Okay, I think that's it. Yeah, that's 3.3 next. All right, well, thanks for tuning in.